This video, we're going to take a look at drawing an electrochemical cell. And when we draw the electrochemical cell, we're going to make sure we have each half cell, right? Because remember, electrochemical cell is made of two half cells. In a half cell, we should have an electrode and an electrolyte solution that the electrode's sitting in. Our electrodes are typically connected by a wire, where that would then go to our circuit, whatever we were trying to operate from that electrochemical cell. For the drawings that we typically do, we usually just put a voltmeter in place just to indicate if you want to keep track of the cell voltage. That's why they might have that there. And what we're also going to do is we're going to look at what are the reduction oxidation reactions that are taking place so we can write out the balanced net reaction here. Okay, and I think for this one, we'll try a salt bridge design instead of our porous barrier. So if we look at our cell notation that's given, you'll notice that we've got our zinc. That's going to be our zinc solid is our one electrode. And on the other side, you'll see the silver solid. That's going to be our other electrode. So when we set up our cell, we know we're going to have two containers here. And once we get our two containers, we've got our two electrodes. So one electrode in each container. So let's make this the zinc electrode. And we're just going to connect it by a wire. I'm going to put a voltmeter in, as I said. And then it's connected to the other electrode, which, based on the cell notation, the other electrode that's being used is silver. Okay, so there's our two electrodes. And we know that in the container, as we said, that there's going to be a solution. And we also need our salt bridge. So I'm going to draw in my salt bridge here, using our what we call a U-tube. This was before U-tube was cool. I'm going to use sodium sulfate in my salt bridge, not just to represent the opening there. And we've got our other half cell with its aqueous solution. And we're all set. So there's our sort of general layout. Now looking at our cell notation, we see that we've got zinc ions and we've got silver ions. So in the zinc half cell, we're going to have zinc ions floating around, right, dissolved in solution here. And remember that this typically is done by, it's a salt solution, right? We can't just open a container of zinc ions and drop them into water. So we want some soluble salt. So a lot of the time you'll see that we use nitrate salts when we create these solutions. So I'm just going to draw in a couple nitrates just to recognize that they're there. Obviously, there would be two nitrates for every zinc if we were keeping perfect track of everything. But I just want to get the idea that those nitrates are in there. So I'm going to draw a few. On our silver half cell, we'll have our silver ions. So I'll draw in a bunch of those. And again, we want silver in solution. We can't open the container of silver ions, so let's use a nitrate salt. We know with it being a nitrate salt that it will be nice and soluble. Right, so there's our two half cells all set up. This is the general setup of what our cell would look like. Now we want to figure out what's happening in each half cell, right? What reactions are taking place. And this is where we need to look and figure out which of the two substances, zinc and silver, is more reactive. And so using your activity series, you'll notice that zinc is typically higher on your activity series than the silver. And so we're going to see that particular metal donate its electrons. Okay, so zinc is going to donate its electrons to the silver ion. So if zinc is giving away electrons, if you remember your redox chemistry, losing electrons is oxidation. So we know here that on this side, in this half cell, we've got oxidation happening, where our zinc solid is going to give off its electrons and form zinc ions. So that's what we should see happening in this half cell. So what that looks like from an ion standpoint is we would see zinc ions coming off of the electrode. So we're going to see an increase in this half cell of zinc ions. And by doing that, what you end up seeing is that over time, the zinc electrode is going to corrode. It's going to come apart. It's going to get smaller and smaller over time. So you might see it actually sort of shrink in size over time. Now, If we do this, our zinc ions are going to build up in this half cell, and that's going to create a very positive scenario in our half cell, which we don't want. We want our half cells to stay neutrally charged. That's why we have our salt bridge. By staying neutrally charged, it allows ions to migrate. It allows electrons to move. Those are all charged particles. We want to end up with this balanced charge. So this is where our salt bridge comes into play. If the electrode is through the oxidation process giving off a bunch of zinc ions, this half cell becomes really positive. We need negative to offset it. And that's where our sulfate comes into play. Sulfate ions from our salt bridge can migrate down into this particular half cell to offset all those zinc ions that are coming in and keeping that half cell neutrally charged. So this is really what's happening in this half cell. And at the same time this is happening, we've got electrons moving, right? Electrons are moving. The zinc is giving them off. The electrons are going to be moving through the wire. So I'll just use a little arrow to show my electron movement through the wire over to the silver electrode, so that the reaction with the silver can happen over here, right? So this is sort of what's happening with this first half cell. Now, one other thing I want to bring out is sometimes we want to label these half cells as anodes or cathodes. Which electrode would be the anode and which one would be the cathode? And this is where there's that little memory trick. A red cat ate an ox. So red and cat go together. Reduction is the cathode, and ox, the anode, is oxidation. So this is actually wherever oxidation occurs, that's going to be always occurring at our anode in our electrochemical cell. So oxidation always happens at your anode. And if you think about labeling of terminals on like batteries, right, because batteries are an electrochemical cell, this would be your negative terminal. Okay. So sometimes we label that on our diagram as well. So we figured out this is the anode, which means then on our other half cell, the silver electrode must be the cathode. And if we've already got oxidation happening, we know reduction has to be happening here. Okay, so silver is being reduced. That means that silver ions that are in solution are going to take an electron and become silver solid, right? So when we look at this particular half cell, we're going to see silver ions moving towards the cathode. And this is kind of helpful in the name of cathode as well, is that cations, which are positive ions, tend to migrate towards the cathode. Okay, so we'll see positive ions moving toward the cathode. And so those positive ions move towards the cathode, the electrons are coming in and they're able to react and they're going to create solid silver, which means essentially we're going to start building up a layer of silver on the outside of this electrode. So this electrode is actually going to get larger and we will see silver solid build up on the outside of that electrode, right? Now, as we said, we want our half cell to maintain its neutral charge. If we start pulling out positive ions out of solution here, this half cell is going to end up very negatively charged. We don't want that. Electrons that are negative aren't going to want to move towards a half cell that's negatively charged. So we need to keep that neutral charge. So that's where our sodiums come into play. Our sodiums can migrate from our salt bridge to balance out that positive charge. And if we leave it long enough, even the nitrates can start to move towards the anode side, right? And zincs that are in the zinc half cell could end up migrating all the way over to the silver side if you leave it long enough. So there is that possibility of that happening. But our salt bridge is the key. It's allowing that continuous flow, right? We have to have a complete path in order for our electrochemical cell to have that flow of electrons. So we've identified our cathode, we've identified our anode, we know where oxidation and reduction are happening. We can label this. This would be our positive terminal on our electrochemical cell. So think about a battery, the positive terminal of your battery. The cathode is the positive side, the anode is the negative side. The anode is always where oxidation occurs, the cathode is always where reduction occurs. So this is our electrochemical cell. This is really what's happening in that electrochemical cell. The last thing, sometimes we like to keep track of is what's the overall net reaction. And we say net reaction because we're not concerned about the nitrates that are in there. They're just spectators. They're not doing anything. The sodium and the sulfates, they're spectators. They're not doing anything. We're focusing on the reaction, and the reaction is involving zinc and silver ions. So zinc is going to give off 2 electrons. Silver only needs 1. That means we really are going to have 2 of these silver reactions happening for every 1 of the zinc. So when we look at the reaction, we're going to have zinc solid reacting with silver ions. And that's going to produce silver solid and zinc 2 plus ions. And to be balanced, we want to make sure that the electrons that are being transferred is equal. So if we are giving off 2 electrons at the anode, 2 electrons are coming to the cathode, we would really be doubling this reaction. So we're really going to need 2 silvers in our balanced net reaction. And that's it. That's our balanced net reaction for the redox reaction that's taking place in this cell.